Hi there. Let's talk about hydration assessment. How can we assess how well hydrated we are? So before we get into that, let's discuss some terms. So let's discuss the difference between water intake and hydration. Two terms that many people use them reversibly, talking about exactly the same thing. They tend to use synonymously the water intake and the word hydration. So water intake, when we talk about water intake, we talk about the nutrient of water. So the water molecules that could be pretty much in every food. So 80%, or most of us, 80% of the water that we consume comes from liquids, and about 20% of that comes from solid food, like fruits, vegetables, bread, rice, pasta. All foods have water. Hydration, on the other side, refers to how well your body is hydrated, how much amount of water you have in your body, what is the state of your body homeostasis, what kind of biomarkers we use to assess hydration. And I like to make an analogy. So you have water intake from one side, and then the outcome is hydration. You drink adequate amount of water, you have optimal amount of hydration. And of course, you have in between the environment, genes, your body size, your nutrition, and that could impact how well hydrated you are based on how much water you drink. On the other side, we have a paradigm that I'm trying to make is that we have physical activity and fitness. So physical activity is like how much exercise you do, how many steps you do per day, what are the minutes per week that you do. And on the other side, we have physical capacity. So we have your endurance, your strength, your VO2 max value. So you need physical activity to build your VO2 max, but of course it depends on your size, the environment, the genes, your nutrition, etc. That could have an impact. So think a little bit of water intake and hydration equivalent of physical activity versus physical fitness. A few more terms that I wanted to discuss with you is like total water intake. So we say 100 ml of milk, just to get an idea, has about 89 ml of water. So about 90% of milk is water. 100 ml of water, it is 100% of water, okay? 100 ml of coffee, if you don't add sugar or milk or anything, it's 99 ml of water. 100% of a cola drink, it's 90 ml of water. So the rest of it is about 10-11% is about sugar and some other additives. 100 ml of beer is 92 ml of water. Hydration, we have different terms. We have the term euhydration, referring to your body have optimal or good amount of hydration. So this is where you want to be. We want to be euhydrated. We use the term dehydration or hypohydration, referring to the water deficit. Some people are using the word dehydration as a process, the process of losing water. So I'm exercising in the heat, I walk around, I hike in Phoenix in the summer, and I'm getting dehydrated. And this is the process of losing water through sweating. And hypohydration, it seems they suggest that hypohydration is the state where you are, the condition. So dehydration being the process and hypohydration being the state. Overhydration, on the other side, is having more water than what your body really needs, which is something which is quite difficult to achieve because your body has mechanisms that as soon as you overdrink, your body increases urinary output. So you suppress antidiuretic hormone and urinary output increases tremendously in a quite short period of time. So you end up running to the bathroom constantly if you're drinking nonstop. And underhydration is a condition that we will discuss a little bit farther at the end of the presentation, but it's the condition where you're not drinking adequate amount of water, but you are not in a state of dehydration. So in my mind, underhydration is something equivalent of what we say pre-diabetes. So you are like on the yellow light, but not necessarily at the red light. So you're one step before you start getting dehydrated. where your homeostatic hormonal responses are activated, so vasopressin is elevated, but your body doesn't have a water deficit, which is the definition of dehydration. You have lack of water in your body. Total body water is down. Let's start discussing hydration assessment during exercise, because there are some differentiations and it will facilitate our discussion later on. So we have discussed already that during exercise, most people don't drink that much. And drinking, as Pete named it back in 1944, he said, drinking during exercise is rarely above 2/3 of net water losses. So we end up drinking significantly less than what we really lose via sweating. And Adolf mentioned that thirst is an inadequate stimulus for drinking. And that term has been coined by many people. Greenleaf was one who studied it extensively, and he called it at the beginning voluntary dehydration, and later on he referred to it as involuntary dehydration. We'll talk a little bit more about it when we discuss later on about dehydration and exercise performance. So dehydration, especially during exercise, the gold standard of how to assess percent of dehydration is based on body weight changes. So changes in body weight to a great extent represent changes in water content. So acute weight loss reflects water loss. Of course, it's not 100% exactly what you lose really reflects to dehydration. So, but it's very, very close. There are some factors that we have to take into consideration, and there is an interesting article that was published actually more than about 15 years ago by Ron Mon that he talks about some potential pitfalls. But overall, changes in body weight is what we use as a gold standard. The only thing that we have to pay attention is we have to have a good euhydrated baseline, and we have to talk for acute weight loss changes, not long-term, because chronic weight loss may reflect not only water, but reduction in fat, with or without changes in muscle. So it could be a response of you gaining or losing weight, and it might not really reflect solely changes in body water. In a laboratory setting, we quite often use changes in body weight to precisely manipulate or induce certain degree of dehydration. This is actually a short video from one of my experiments in the lab, where if you pay attention actually in the lower part of this video, you'll see that the whole bike is mounted on the top of a large scale, very similar to the pet scales when you take your dog to the vet. So we have put the whole bike on the top of the scale, and then without getting the subject off the cycloergometer, we can ask them to stop spinning and take their body weight fairly quickly, so we can see how much they lose while they're exercising in a hot environment. Moving forward, as we mentioned already with dehydration, we extensively spoke about changes in osmoreceptors and in baroreceptors, and I have shown you already multiple times this diagram and all the responses. So it's natural to think of what we can measure in the blood to really identify dehydration. So one of the things that we can measure is changes in plasma volume. And with changes in plasma volume, we can assess the percent change of water content in the plasma. So this is the paper actually by Dill and Kostel that it was published back in 1974, many years ago, where they propose an equation that you can use to calculate the percent of plasma volume as a response to dehydration. So plasma is the watery part of the blood. If you centrifuge blood, you have the cells on the bottom, you have a thin layer, much thinner actually from what you see here, with white blood cells and thrombocytes or platelets, and then on the top you have plasma. So you can measure what is the percent of plasma and how much the plasma changes, because with dehydration you lose water from the plasma as well. So blood becomes more concentrated. The only issue that you have to have a very good baseline of euhydrated plasma assessment. So you have to know exactly what is your hematocrit and hemoglobin when you are euhydrated in order to make this kind of calculation. So you need a pre-euhydrated sample, and then you can have a post-dehydrated sample to be able to make those type of comparisons. Of course, you can assess one of the main stimulants of thirst and vasopressin that it responds to dehydration, which is plasma osmolality. And this is actually a short video of an osmometer that we have here in the lab, the A2O, a large automated osmometer that we use to assess plasma or urine osmolality. Plasma is usually between 280, 285 to all the way 295. This is the normal plasma osmolality. The units are millimole per kilogram of water in the plasma. These are the SI units, and also milliosmol per kilogram of water. It's also another unit that has been widely used, which is equal to millimole per kilogram. Usually, most people agree when plasma osmolality is greater than 295 or 300, then it indicates that it's used as a diagnostic criteria for dehydration. As you understand, taking blood samples is a little bit more complicated. So throughout the years, different things have been suggested to be used instead of taking blood samples, and one of them was tear and measure osmolality in the tears. And the thinking behind that was that the tears is produced from the interstitial space, and those fluids should have very similar osmolality to the osmolality that you have in the interstitial space and to the plasma. So there are some data that indicate that it can be used. Tear osmolality could be a potential marker of hydration, especially when you have a significant percent of dehydration. Saliva, it's another thing, and we know when we get dehydrated, we run out of saliva, or our saliva becomes much thicker. So this is something that has been also used, measuring osmolality in saliva, which is much easier to collect and to analyze, and it's not invasive. You don't have to take blood samples, and it could be quite easily used in children or in vulnerable population when blood sampling it's more difficult. So let's move now on assessing hydration, not during exercise, but rather at rest. And usually at rest, people are not dehydrated. People are not walking around with 1 or 2 or 3 or 4% dehydration, unless they have a clinical condition, okay? And potentially in some cases with older adults that in combination with drugs or heat exposure, it might be the case. But for many people, as I showed you earlier, many people do not drink enough and do not drink, at least according to the dietary guidelines. So let me walk you through these cases of what euhydration is and different types of dehydration. So first of all, just to explain you these diagrams, we have blood osmolality on the top, blood volume, cell volume, behavior, and the behavior refers primarily, am I thirsty or I'm not thirsty, and also whether you have vasopressin secretion, AVP or vasopressin secretion. So when somebody is euhydrated, blood osmolality is normal, blood volume is normal, cell volume is normal, and we're not thirsty, and vasopressin is low, and quite often even non-detectable sometimes when you're trying to measure it. So we have two different types of dehydration. We have what we call cellular dehydration and we have volume dehydration or extracellular dehydration. And the difference here is that with the cellular dehydration, we have high plasma osmolality versus no differences in plasma osmolality here. Blood volume is the same. Cell volume is low, so cells are shrink. We are thirsty, and we have high vasopressin. So quite similar, I would say, phenotype here, although blood osmolality is not changed, blood volume is low, so we have better receptor activation. We're thirsty, and we also have what is called salt appetite. So as a response to hypovolemia, you get increase in sodium appetite and salt appetite, and vasopressin is also elevated. This is actually, in my opinion, this is probably the most important and the one that I would like to stay a little bit longer. This one where we have a cell and volume dehydration at the same time. So in this case, and this is what happened, especially during exercise, during exposure in the heat, etc. We have both increased plasma osmolality, and we also have decrease in blood volume. So we have what we call hyperosmotic, increase in blood osmolality, hypovolemia, decrease in blood volume. We also have shrinkage in cell volume, where thirsty and also salt appetite is increased. And of course, if we measure vasopressin is stimulated. So let's pay attention now. What happened if you are just a small drink? And I'm not talking about not drinking any water, okay? I'm not talking to somebody that is like intentionally or unintentionally doesn't have access to water. But I'm talking about somebody who just consumes small amount of water. So blood osmolality doesn't seem to change. So we have about the same blood osmolality. Blood volume, based on what we know today, it doesn't seem to change either. Cell volume seems to remain unchanged, and we're not thirsty. This is the condition that I call underhydration. However, if we measure vasopressin is stimulated. So let's check out this study. Very interesting study with a lot of cool data. So in this study, they used the model of high and low drinkers. So they took two sets of people, one of them that they self-declare as being high drinkers, and another one that they were low water drinkers. Okay, when I say high and low drinkers, I'm referring to water intake. So the low drinkers are the ones with the dark data. They showed that the low drinkers had very high urine osmolality, and the high drinkers had very low urine osmolality, as you can see here on the y-axis. And what they did, they measured them here at baseline to confirm that they were high and low drinkers based on the urine osmolality. Then they took the high drinkers and they decreased their water intake, and they observed that when they decreased their water intake, urine osmolality went up. Then they took the low drinkers that they had high urine osmolality, and they increased their water intake, and their urine osmolality went down. So the ones that they were drinking a lot of water, when they decreased their water intake, urine osmolality went up, and their body was trying to conserve water. The ones that they were low drinkers, when they increased their water intake, urine osmolality went down, and they started producing more diluted urine, and you can see that it remained low. Then they stop after 4 days, and they allow them to recover, and you can see that the numbers went back to similar. So from the low drinkers, the urine osmolality went up. The high drinkers, that they were drinking small amount of water, they started drinking more, and the urine osmolality decreased. So let's pay attention here in this very interesting point. The interesting point is here. Look at the serum osmolality, which is those, the data, the circles right in the middle. Whether you were a high drinker or a low drinker, whether you changed or did not change the amount of water you're drinking, the serum osmolality remained the same. So serum osmolality didn't seem to change as a response to drink more or less water, which is really interesting. So let's pay a little bit attention in this diagram. We have again the high drinkers here, that they have low plasma AVP in this diagram. We have arginine vasopressin. We have the high drinkers here. The low drinkers are up here with significantly higher arginine vasopressin. When they start drinking more water, you can see vasopressin decrease. When the high drinkers decrease their water intake, their vasopressin increase. And when they return to the pre-baseline values, you can see the vasopressin values kind of bounce back to where they were before. So one of the ways to assess hydration for a long time has been, let's assess total body water. So how much water we have in our body. And we have different techniques that we can do that. We can do it with a stable isotope, like deuterium oxide, which is stable isotope, it's not radioactive. You ingest a small amount of water that instead of hydrogen, it has the heavier isotope of hydrogen, which is hydrogen 2. And then based on the amount of dilution, you can go, after equilibration, you can take a urine or sweat or saliva or a blood sample. And based on the dilution, you can figure out how much is your total body water pool. You can also assess that with bioelectrical impedance. You can do a BIA analysis, bioelectrical impedance. Most of the body scales now, even those that you have at home, have this type of technology that they can tell you how much water you have by passing a small amount of electricity through the body. And also, if you have a DEXA scan, based on the DEXA scan and the body composition, you can also set total body water. So you can measure total body water. One of the problems, though, is that by telling you how much water you have, it doesn't really mean anything. So if I tell you that you have 15 gallons of water or 40 liters of water in your body, what does it mean? Are you well hydrated or you're not? Are you drinking enough or you're not drinking? So it doesn't really tell you much because we don't really have very tight ranges that we can use as standards to compare with and define what is well hydrated and what it is not. The other idea, of course, is to measure urinary biomarkers, and the idea comes from ADH, arginine antidiuretic hormone, or AVP, the arginine vasopressin. We know that ADH is secreted by the posterior pituitary. It has an impact in the kidneys. It increases water reabsorption, and as a response to the water reabsorption, we have higher urine osmolality, so you have more concentrated urine. So this is a relationship between vasopressin and urine osmolality, and you can see as vasopressin increases, you have at the beginning a linear relationship between AVP and urine osmolality, and then after actually a quite low level of vasopressin, your body reaches the maximum urine concentrated capacity. So even if you get more dehydrated, and even if vasopressin increases beyond 4, 5, 6, 10, 11, 15, 20, etc., urine doesn't get any more concentrated. It gets very dark, almost looking like what I like to say, your urine looking more like apple juice than lemonade. But this is the idea about measuring urinary biomarkers. And one advantage with the urinary biomarkers is that those biomarkers are very sensitive, and you see changes in urine composition, even with very low, very small changes in arginine vasopressin, which is what happens when you change your water intake. So you can measure 24-hour urine volume. So we don't have very strict guidelines on how much is too little, or how little is too little, or how much you're supposed to drink. So we don't have any numbers based on the urine volume that we can say if you pee a certain number per day, this is a very small amount. However, in general, we say somebody that produces less than 1 liter per day, we say this is a good sign of you're not drinking enough fluids. I have some data that I can show you in a little bit about how much you pee and how often you pee being like one of the biomarkers that we use. Of course, we can measure urine osmolality, and we like to measure 24-hour urine osmolality because it gives you an overall assessment of how your body handles water in a day versus just taking a snapshot of a urine sample on a specific time point. There are multiple different values that has been used in the literature. 800 is widely used as a level of underhydration. 700 is something that was introduced by the American College of Sports Medicine many years ago, indicating that when your urine is more concentrated, that 700 milliosmol or millimole, it shows that you're not in optimal hydration state. And also, more recently, we have several studies that indicated that when your urine osmolality is below 500, then this is an indication of optimal water intake. You're drinking enough, your body is very well hydrated. So 500 has been used as the level of optimal hydration state. One of the disadvantages of urine osmolality is that it requires expensive laboratory equipment. And probably for this reason, we have been using more often the assessment of urine-specific gravity instead of urine osmolality, which is easier to assess. You can have an optical refractometer or a digital refractometer, and also you can use one of those urine strips where you can immerse one of those strips in urine, and then you can compare the color and come up with urine-specific gravity. Even though, to be perfectly honest, this is not very accurate, and we published a study a few years ago indicating that it's probably not the best way to assess hydration by using those strips. There are some cutoff points. The American College of Sports Medicine of underhydration is around 1.020. The inadequate water intake or optimal hydration is supposed to be below 1.013. This is the equivalent of the 500 millimole per kg that I was referring to urine osmolality earlier. So moving from more complex to more practical and easier to assess techniques, let's talk about urine color. So urine color was introduced back in 1994, was the first study, and 1998 was the second validation study. It was introduced by Larry Armstrong, professor from University of Connecticut, and I had the luck to work very closely with Larry Armstrong. He was my PhD mentor, and we still collaborate. So he came up with this idea of identifying those 8 color from number 1 all the way to number 8, with the first urine colors from 1 to 3 indicating good hydration or euhydration, and then as the color getting darker, then indicating that your body is trying to survive, trying to hold as much water as possible. And I know you might be thinking, what is that green color urine? And believe it or not, there is urine that could be that dark or even darker sometimes, which is not only an indication of hydration state, but also speaks to potentially muscle damage and a condition that is also known as rhabdomyolysis. So overall, that the urine color chart, the Larry Armstrong 8-level urine color chart, has been very widely used and has been validated in athletes, in young adults, in older adults, in pregnancy. We did this study where we validated in children. So it's very widely used, and it's a way that you can use to overall assess hydration, and it's, I would say, highly recommended. I mentioned earlier that the 24-hour urine volume, it's also an indication of hydration status. So this is a study that we did with colleagues from University of Arkansas. And we found that the number of void in a day also can be used as a way to assess hydration. So we had different groups of euhydrated and and hypohydrated people, and we compared them, and we found statistically significant differences between those two groups. Lately, actually last year, we published a study where we did a statistical analysis known as ROC analysis, or receiver operating characteristics analysis, where we tried to identify the threshold by which we can identify good hydration if we combine two different biomarkers. So we wanted to combine the urine color and the number of voids together and see whether those, when they're combined together, will give us better information. So we did the assessment in children. We used 210 children, and we also use here 102 adults. We wanted to see whether we could assess underhydration by using urine osmolality greater than 800. And we found that when we combined both of those, the overall predictability of the model was 0.89, so 89% overall predictability, and the sensitivity, or the ability to identify correctly people that they were underhydrated, it was 1.0 or 100% in children, and very similar data for adults. 97% the overall prediction model, and 100% sensitivity on correctly identify people with urine osmolality over 800 just by combining urine color and void. So we said more specifically, if you're going to the bathroom less than 7 times, and if your urine color is dark, then that is an indication that you are underhydrated. And for children, that number, the number of visits was 5, was a little bit smaller. Some people have suggested that you can combine different biomarkers, practical biomarkers, to assess hydration. And this is something that Sam Severon came up with this idea, what is called the WUT, or the WU2. W is the weight, so weight loss. If you weigh less than usually when you wake up in the morning, if your urine is very concentrated, and if you are thirsty. So if you have a combination of those, if you have 2 of those, you're likely to be dehydrated, any combination of 2 of those. And if you have a combination of all 3 of those, it's very likely that you are dehydrated. Of course, in the field of hydration, like in every scientific field, there is quite often controversy and disagreement. And here is actually, I have a paper from a colleague of mine, Tamara Hugh Butler, where she presented a very interesting study. She took about 300 blood and urine samples, and she was trying to use what people say concentrated urine, and some people use the term dehydration, which I agree with Tamara. Dehydration doesn't exist when your blood biomarkers are not indicating that you are dehydrated. So dehydration, as I said, as we discussed earlier, dehydration is a water deficit. When you do have a significant water deficit, your blood biomarkers are affected. So this is what they did in this study. They took dehydrated subjects according to more than 700 milliosmol per kilogram using the American College of Sports Medicine cutoff point. And they called the subjects that they had concentrated urine as dehydrated. And they took the ones with less than 700 and they called them hydrated or euhydrated. And they measure plasma sodium, serum potassium, serum osmolality, urine osmolality, and urine-specific gravity and thirst. And what they found, actually, which is very interesting, they found that not much significant differences between osmolality. Small difference, yes, it is significant, but probably not that clinical significant when the difference is like not even 1 millimole per liter. Large difference in urine sample, they classify the subjects like that. So 900 something versus about 400, the dehydrated versus the hydrated subjects. But the point that they were trying to make, it was that dehydration is like how you define it. So if you define dehydration by just looking at urine color or urine concentration might not be the best way to assess hydration. So this is a potential pitfall that many scientists have been through. We say that dehydration leads to concentrated urine biomarkers. So urine osmolality goes up, urine color goes up, urine specific gravity is up. So the question that we're asking is, does concentrated urine means dehydration? So this way it works. We agree that dehydration concentrates urine. Thus the opposite is correct. So if we have just concentrated urine, does this mean that it is a sign of dehydration? So this is something that I don't think is the case. It is a sign of something, but it is not a sign definitely of dehydration. It is not a sign that you do have a water deficit, which is the definition of dehydration. So I came up with this paradigm of this idea of underhydration, and I wrote this article trying to describe what underhydration is, and I propose this state or condition where you have a inadequate water intake, so small amount of water intake. Total body water is not affected, so your body is able to maintain total body water. You're not thirsty, your plasma osmolality is not different, but your vasopressin is elevated and your urine concentration is higher. So this condition, I like to call it underhydration and not dehydration, because most of the time you don't have water deficit. And this is what I like to call a state equivalent to, I like to compare this condition to pre-diabetes versus diabetes, like underhydration being a condition equivalent to pre-diabetes and dehydration being a condition like diabetes. So maybe think of underhydration as a state of pre-dehydration, a state where you're not dehydrated, but you're getting closer. Your body is responding by secreting more vasopressin to maintain water homeostasis. So the bigger question that we won't discuss today, but we will definitely discuss later on, is whether being in that condition of underhydration, being in that state with elevated vasopressin, does it put you in a risk for chronic disease, longevity, well-being, good mood, cognitive function, and on and on and on? And I think we have a lot of data that the answer, I think, so far, what I start to believe is that the answer is yes. Living in that condition, you are at risk or significantly greater risk of many chronic disease, potentially longevity, and many other conditions. So before I close, I have one more thing. Like Tim Cook and Steve Jobs used to say in their Apple presentations, which is wearables. And I don't know how many of you have watch those live presentations that Apple is doing every year when they have a new product. But more than 6-7 years ago, when the first Apple Watch was introduced, Tim Cook said that Apple Watch would be able even to measure hydration. So he made that statement, and up to 2022, up to today, Apple Watch cannot measure hydration. So it was something that, in my opinion, was very interested, and everybody was very optimistic that they will be able to measure hydration, but we don't have such a unit right now. At least Apple Watch cannot do that. There are multiple products in the market that some of them, they still exist, some of them that they disappear and you cannot find them anymore. LVL was one of the first ones that came out promising that can measure hydration. More recently, there is a company which is called Rockley Photonics that they have already published in their website some preliminary data indicating that they do have a system that they can measure hydration with very high sensitivity and specificity. And just out of disclosure, I'm collaborating with this company as a scientific consultant. So I just wanted to declare that since we're talking about hydration assessment. Many other companies, they're looking into different hydration biosensors by using patches that they glue on the skin, and they can measure different things to assess hydration. Nix is one of them. Epicor is another one. Epicor is the company actually that developed the Gatorade hydration sensor that they have, and you might have seen that. It is right now commercially available, and it doesn't measure hydration per se, but it can estimate sweat losses, and it can estimate electrolyte losses via sweat. That could be very helpful for people that they are athletic and they exercise in the heat for a prolonged period of time. So this is something very interesting. Other companies are working on similar sweat patches. GE is involved in this game. Some other companies I'm aware that are involved in this game. And of course, we have a series of water bottles and smart and less smart water bottles that are in the market. Hydrate Spark, Pool Hydrate, and different ones. Some of them that they talk to your phone, other ones that are just some plastic with the dial that tells you how much water you drink. So before we wrap up and we close this presentation, I want to tell you a small story. So before closing, I would like to bring something just to think about. Is like, it's many times we're stuck with what we can really measure, but not everything that counts can be counted, as Albert Einstein said. So we keep measuring osmolality, we keep measuring plasma volume changes, renin, angiotensin 2, aldosterone, vasopressin, cupeptin, just because we can, just because it can be measured. But many times looking at those, it might not really mean much, at least as far as assessing hydration state. So we might have to start thinking outside of the bubble and outside of the box, trying to identify simple and practical biomarkers to assess hydration, because one of the issues with hydration is that hydration can change significantly from one day to the other. One day we might be at home, not too much active, in a nice air-conditioned room, or in the middle of the winter where we're not really sweating much, we don't lose much water, and our water needs are very small. And another day we might be out hiking in the woods in a very high heat, etc., and our water needs might be really high. So we have to come up with ways to really assess hydration with simple, practical, and reliable biomarkers. Thank you. And let me know if you have any questions.